between viscosity and solid friction? Number one, both oppose relative motion. Number two, both are dependent on the nature of the surface. Differences between viscosity and differences between viscosity and solid friction. Number one, solid friction occurs in solid, while viscosity occurs in fluid. Number two, solid friction is independent of surface area, while viscosity is dependent on surface area. Number three, solid friction is unaffected by temperature, while viscosity is affected by temperature. Alright, so now let's quickly look at the Newton's law of viscosity. Newton's law of viscosity. According to Newton, the drag force F experienced by an object in a fluid, in a viscous fluid, is proportional to area and is also proportional to velocity gradient. By the time I remove this proportionality sign, I get F is equals to a constant K, area, and velocity gradient. Velocity gradient is equals to velocity all over distance. So which means for an object that is falling from up to down, it becomes change in velocity all over change in distance for the vertical distance. So by the time I put that inside, I'm going to get F is equals to K, A, D, V all over dy. Now, this K is equals to coefficient of viscosity. By putting this inside, I get F is equals to coefficient of viscosity, A, dV all over dy. This is the first equation formula that we get from Newton's law of viscosity. Now, by the time we divide both sides by this surface area A, we are going to get F all over A is equals to coefficient of viscosity, dV all over dy. F all over A, force over area, is stress. So stress is equals to coefficient of viscosity, dV all over dy. This is the second formula that we derive from the Newton's law of viscosity. Let us look at Stokes' law of viscosity. Stokes' law of viscosity. According to Stokes, when a spherical metal ball is brought in a viscous liquid, this is a spherical metal ball, and this is the viscous liquid. The weight of the ball is acting downward, with W of the ball acting downward. This ball is being acted upon by two forces acting upward. The first one of them is the viscous force, while the second one is the upthrust. The ball is acted upon in upward direction by viscous force and upthrust, while the weight of the ball is acting downward. According to Stokes, when a ball is first dropped in a viscous liquid, it first accelerates before moving with a uniform velocity known as terminal velocity. Let's look at it. If you plot a graph of velocity against time for an object that is falling in a viscous fluid, you are going to get this before the thing becomes constant. The velocity will keep rising, and on getting to the terminal velocity, it remains constant. From here to here, there is acceleration. But immediately we get to the terminal velocity, acceleration becomes zero. This is the graph of velocity against time for an object that is falling in a viscous liquid. Good. Now, from this, according to second equation of motion, second law of motion, we have F is equals to ma. F is equals to ma. Now, this F represents all the forces that are acting on this ball. Now, if I'm to take it into consideration, the coordinates we have, this is positive y, and this is negative y axis. This is positive x axis, and this is negative x axis. Now, as it is, this weight is acting downward. This is the weight acting downward, as in the weight is in negative y axis, negative direction. V is acting upward. V is in this direction. That is, V is a positive. U is acting upward. It means that U too is a positive U. So if you take these forces into consideration now, then my F is equals to minus W plus V plus U. And that will be equal to what? M what? MP. By the time you multiply by this minus, you are going to get F is equals to W minus V minus U is equals to what? MP. Then remove the F out. Then you get W minus V minus U is equals to what? MA. Now, when the ball is falling with uniform velocity, known as terminal velocity, at terminal velocity, acceleration is equals to zero. So we have W minus V minus U is equals to what? M bracket 0. Mass times 0 gives me 0. So I have W minus V minus U is equals to 0. Now, all these ones that have negative, bring them to the other side. Take them to the other side. So you get W is equals to V plus U. What can you deduce from here? You will see that there are two upward forces, U and V. And there is a downward force, W. So which means at terminal velocity, there is equilibrium between the downward force, W, and the what? Upward forces, viscous force and upthrust. So at equilibrium, upward forces equals to downward force. That is, V plus U is equals to what? W. Now, from there, recall that W is equals to mg, weight of an object, which is the gravitational pull on the object, is equals to mg. Also recall that density rho is equals to mass over volume. Now, if you want to express mass in terms of density and volume, you get m is equals to density times volume. Now, the spherical ball that is dropped is spherical. The ball is spherical in shape. The volume of a sphere is equals to 4 over 3 by what? By r cube. That is the volume of a sphere. Now, inside this W, which is the weight now, insert all this inside. So you will get W is equals to rho Vg. And that is equals to rho, volume is 4 over what? 4 over 3 by r cube in G. Call this one equation 1. Also, upthrust is equals to mg. Now, by the time you convert m to a term involving density and volume, you still get this. But mind you, to differentiate the density of solid that is falling in the liquid and the density of the liquid of fluid, then we use another sign for density. This time around, we use sigma to represent the density of the fluid, and that is equals to mass over volume. From there, mass is equals to density times volume. The density, the volume of a sphere is equals to 4 over 3 pi r cube. Putting it inside, we get U is equals to density, volume, and G. From there, we have density 4 all over 3 pi r cube G. According to Stokes, experimentally, V is equals to 6 pi r V naught coefficient of viscosity. Experimentally. This is the what? This is an expression for the viscous force experienced by an object in a fluid. So now, equation 3. Now, according to the equation we got at equilibrium, W is equals to U plus V. Our W is equals to density 4 all over 3 pi r cube G is equals to U, which is density 4 all over 3 pi r cube G plus 6 pi r V naught coefficient of viscosity. Now, those ones that look alike, bring them together. So you take this to this side. So by solving, you get density 4 all over 3 pi r cube G minus density 4 all over 3 pi r cube G is equals to 6 pi r V naught coefficient of viscosity. What is common? Take the common factors out from here. So we get 4 all over 3 pi r cube G. What is left here is density. What is left here is only what? Density. This is the density of the solid, while this one is the density of the fluid or liquid. And that's equals to 6 pi r V naught coefficient of viscosity. From there, pi we cancel pi. 1r, we cancel 2r here, it will remain 2. It cancels 1, it remains 2. And from there, we use these 3 to multiply what is here. So from there, we're going to get, when we cross multiply, we get 4r squared G. Coefficient of the density of solid minus the density of liquid is equals to 18 V naught coefficient of viscosity. 2 here 2, 2 here 9. So I get 2r squared G coefficient density of solid minus density of liquid is equals to 9 V naught coefficient of viscosity. By making the coefficient of viscosity the subject of the formula, we get coefficient of viscosity is equals to 2r squared G density minus density, everything all over 9 V naught is the expression for the coefficient of viscosity of a liquid. Of all the parameters that are inside this formula, eta is the coefficient of viscosity. R is the radius of the ball. G, acceleration due to gravity. Then rho, density of solid, density of ball. Sigma, density of liquid. V naught, terminal velocity. These are the meaning of all the parameters inside the formula we derive for the coefficient of viscosity. Now, let us look at this example. The drag force experienced by an object of area 4 millimeters square falling in a viscous liquid between two parallel plates separated by a distance of 60 millimeters is 15 Newton. If the speed is 20 meters per second, calculate the coefficient of viscosity of the liquid. Let us extract all the parameters in this question out. So we have area is equal to 4 millimeters square. Then we are also given the distance of separation, which is that is dy. You change the y is equal to 6 millimeters. Then we are given speed, which is dv, and that is equal to 20 meters per second. Now, we have to calculate. We are given force. Force F is equal to 15 Newton. We have to calculate the coefficient of viscosity. And that is millimeter square is equal to 10 raised to power minus 6 meters square. Therefore, 4 millimeters square is equal to 4 times 10 raised to power minus 6 meters square. That is the conversion for the area. Now, the conversion for the change for the distance. So 6 millimeter now. 6 millimeter will be equal to 6 times 10 raised to power minus 3 in meters. This is the area. This is the distance, the converted distance. Now back to the formula. F is equal to coefficient of viscosity, A dy all over what? All over the dv, all over the dy. From there, F is what? 15. And that's equal to coefficient of viscosity that we are looking for. Area that we have calculated, and that is 4 times 10 raised to power minus 6 times dv, which is 20 all over dy, which is 6 times 10 raised to power minus 3, become positive. So we have 15 times 10 times 6 times 10 raised to power minus 3 times 10 raised to power 6. So by the time you do the division, this times this divided by 4 times 20, you will get 1.125 times 10 raised to power 3 times 10 raised to power 6. It remains 10 raised to power 3, so we have times 10 raised to power 3. And the unit of coefficient of viscosity is Newton second per meter squared. Let us look at example 2. A spherical metal ball of radius 2 mm and density 1,200 kg per meter cube is dropped in a viscous liquid of density 960 kg per meter cube. If the ball falls with a terminal velocity of 10 meters per second, calculate the coefficient of viscosity of the liquid. Let us write all the parameters given. We are given the radius of the ball, r is equal to 2 millimeters, which is equal to 2 times 10 raised to power minus 3 meters. Then we are also given density of the ball. The density of the ball is equal to 1,200 kg per meter cube. Then we are also given the density of the liquid. The density of the liquid is equal to 960 kg per meter cube. We are given the terminal velocity, which is 10 meters per second. Terminal velocity is equal to 10 meters per second. And we have to calculate the coefficient of viscosity. We have to calculate the coefficient of viscosity. Now, from here, recall the formula which says coefficient of viscosity is equal to 2 r squared g density minus sigma all over 9v naught. This is the formula that we are going to be using in order to get the coefficient of viscosity of the liquid. By inserting the parameters, we are going to get 2 times r squared, 2 times 10 raised to power minus 3 everything squared times g. Our g is a constant, and that is 9.8 meters per second squared. So we have 9.8 density 1200 minus 960 all over 9 times V naught, which is 10. By the time we take it into consideration, we are going to solve this arithmetically. So we are going to have 2 times the square of 2 here is 4 times 2 by 90 is equals to 18,816 times 10 raised to the power minus 6 divided by 90 is equals to 209,067 times 10 raised to the power minus 6. Now, by the time we solve this in terms of the indices, you take this one place to the front, another place, one place to the back, another place to the back. So it means for you to get to this point, you will move it 2 places to the back, and that will affect this minus 6. So this minus 6 will now become minus 4. So that is equals to 2.09067 times 10 raised to the power 2 times 10 raised to the power minus 6. So by the time you solve it, the indices, you're going to get 2.096067 times 10 raised to the power minus 4 Newton second per meter square.